Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Kirk Gray.
Hey, Kirk.
Hey, Fred.
One of the things that crossed my desk in the last couple of weeks was somebody said, and it was like you'd feel in the email. I mean, it wasn't with emojis or anything else, but I've been in these conversations. You know, I'm suggesting we run HALT, and one of the senior engineers went, "What? What a waste of time." You're just going to go break it. And then we're going to be, messing around with stuff that we don't need to be messing with and blah, 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 blah. And they're like, no, Let's just get on with making it reliable. I'm like, it's a palm slapping my forehead kind of emoji at that point. But it was, and I mean, where does this come from? Why does that occur? And you've been through this many more times than I have, I'm sure.
Right. And in fact, I devote a chapter in my book to this fear and what'll happen when the group doesn't understand what the philosophy is, the underlying stress strength diagram, and how the approach from looking at the product strength and using that strength inherent to the product, using, with a normal, centered design, how that enables you to do accelerated testing and quickly, hopefully, identify a weakness in the product. Mm-hmm. So when you're in a development stage of the product, and if you had no previous product history on that particular design, or it's a new design for you, a lot of time you're spending your effort just getting it to work at time zero, just getting the design up and.
Well, that's like a HALT all by itself, isn't it?
Exactly.
We got it. We got the power supply to turn on, and we got this motor to turn. Now the gears are acting up. So you're finding one failure mechanism or failure mode after another, and eventually you get it to work. Now it's time to say, all right, now let's continue that process, right? Let's continue to add stress in a meaningful way and find where the next mechanism is, where the next failure mode is, and then deal with it. But why is, and I've had that happen where, the early prototypes are precious, right? And the early physical things are precious. And so part of and expensive, and they might not be using exactly the right construction methods, or it might be 3D printed versus not, stuff like that. And then you go,
how much relevant?
How relevant is it? And then that, I think that's one of the things is, how do I translate this to our finished product? And sometimes it's a very true thing. Instead of a molded part, we're using a cast part or something like that, or some mock-up that's using a easy to form material versus the stiffer, more robust material we're using in the past. Well, if that fails, then we'll go, let's wait till we get the real one and we'll check that again.
Right. Those plastics, that material could have a different thermal coefficient of expansion. It could have a different softening
tensile strength. It could be all kinds of stuff.
All kinds of strength that would define that. Mechanical strength. And so, when you're building a new system and you don't have a reference design that you've already built or something like that, you're basically going on good design practices. And this is like from a mechanical engineering design point, like a torque on a gear, you have physics models.
Yeah, you can rip that gear right off if you go too hard, too fast on it. Yeah.
But this is part of a CAD system or a design system that would give you a strength margin. You say that the most torque on this will be 30 inch-pounds or whatever. I don't know.
Yeah, there's ways to calculate stuff like that. And then a lot of the CAD programs today have built-in finite element analysis. So you can isolate that and go, here's how much is torque or power we got coming down the shaft, and it gets thrown out this far, and here's how big the gear is. And
And this is how much strength margin you have. I mean, this is what the actual, what our calculations show for the gears, the teeth, and what the most torque is, and why you'll have to have this size teeth and this size gear.
Oh, we're done now. We don't need no HALT. We already know this. So, but I'm being facetious, right?
Right. Because there's always something introduced in the manufacturing of that gear and the particular supply materials and things like that.
Oh, there's assumptions in the model too that may or may not be true.
Right. What's the temperature of the gear? I mean, that'll change the strength also. Mm-hmm. And so, whether it be a seal, a gear, or whatever, you're going to first get it to work at the working conditions you expect it to work. And then you need to consider beyond time zero, how it'll work, how the degradation of either the materials or strength or chemical reaction in something that's going to cause material degradation or fatigue damage.
Yeah. Well, I think that's where part of it comes in. I heard this years ago I think it was, I'm trying to remember who it was. It was a scientist of some sort. And he was like, you have to understand when you walk in the room, you have this dark cloud around you because you come in talking about how things are not going to work.
Yeah.
Me and the rest of the team, we're trying to figure out how to get it to work. We want it to work. And you're saying, well, it might fail here, it might fail here. And so I think, and when you walk in with the HALT and you explain the basic idea of it is, we're going to step stress, until we find failures. And like, well, we don't want failures. We want it to work.
Yeah. Yeah. And this is where semantics may help you. I try and when you talk about failures, it's like, well, that means within the spec or within it didn't reach its expected value or whatever. And the reality is, again, I talk about HALT as highly accelerated limit testing, which is much better terminology because you're finding either operating or sometimes you're finding destruct limits.
Which are my favorite, by the way. I like it when it breaks. But that's just me. Maybe that's that dark cloak around me when I'm walking in.
But you may define a failure as before any kind of catastrophic, as say a seal leakage over time. That you have a certain rate of leakage that you say that's a failed, whereas everything leaks. So you have to expect some leakage at some point, but you may have a threshold. And then you can test different scenarios, temperature and other things, and see if those same limits hold for different environmental stress conditions. And if they do, then you've got an envelope of safe stresses to use to continue to age the product through fatigue, thermal cycling for mechanical fatigue. And if you have the capability to do vibration sometimes, or if it happens to be a system that will be subjected to transport or vibration, that would be something you'd add. But, you build simply first single stress, find those limits, then add to that, keeping the combinations of stresses really until you start wanting to do more fatigue damage. Yeah. And you may have long periods of, active dynamic stress or long dwells, or you may mix the two. And there's really no set guideline or cookbook for that. It's really adaptive to each system. Yeah. And so for those guys that haven't had any systems built, they're really, and they haven't gotten a working system, or you're just in the process of developing, talking about going to limits is pretty scary for them, I believe.
Well, I think that's one source of fear, but I think it's that they'll overcome that is basically it's the same as just trying to get the first one to work. Is you're running into the areas that need improvement. Let's continue that process. And so you can make a very robust product. Now, other things come to my mind as what is behind some of this fear. One of them is that when we talk about, we should do a HALT, we need to discover stuff. We need to find what we think we know is true or not. Right.
Right.
So part of it is that you're you're actually challenging those engineers and their thought process for how they design the product. Well, I know how to do this part. This is a standard gear, blah, blah, blah. It should be able to work just fine. And if we go to the lab, and I ran into this with an electrical product and says, no, the circuit board's real small. It's not going to move. It's going to bend on a single axis. It's not going to do what you're thinking it's going to do, blah, 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 blah. And I said, well, let's just go try it. Let's just go try it. And he was like, he folded his arms and like, you'll see I'm right. Kind of call my bluff kind of thing. And of course, 2 days later, I'm back to him with a high-speed video showing him exactly the behavior that our CAD, the finite element showed it would do. And that motion was a whole lot more aggressive, and it actually broke a bunch of stuff, and called it product fail. And and he had to eat his words essentially in front of the group. And so part of it is personal. You walk in and say, hey, it's like when doing an FMEA, you walk in and say, let's figure out how many ways your baby's ugly. Right? You got to be careful with that, because we're walking in saying, hey, let me take your precious new design concept and just go bust it all up. and I think semantics plays a role in it, but it's an understanding that, I'm trying just to get it to work, and I'm trying to coddle it along until we can go. I think we're both trying to achieve the same thing. It's just that we're going to throw it over a cliff to see if it works. And they're going to say, well, let's just put in 5 volts and 5 PSI and see if that holds for 6 months, and then we'll go to 10 PSI. No, kind of thing like that. So
how much time do you have? Yeah,
that's
exactly.
Right. So I think there's part of that.
And how many samples do you have? That's another thing.
Well, I think that's the other fear, is you're going to take one of these and break it.
And
now I can't use it.
3.
I only have 3, and I can't use them for other things we need to use it for. That's where I think people, getting a whole system and doing the interactions and seeing how the whole system does it, because that's the most complex part. That's, but if I look at just a gear assembly, or I look at just a power supply, if I look at just, one component of how it behaves, one material set, I could still learn a lot.
Right.
Right. And so I think the part of it is that it's, you're challenging my design prowess. Another one is we have limited resources, and we're aiming to break this one. Right. And another, so what else? What other kinds of things trigger this pushback?
I think you've got it. It's the fear that, that they're going to be chasing irrelevant failures because you're breaking it with.
Yeah, that's a different one.
Overstress.
Yeah, I think that's another one. And it's in the books. It's in your book. It's like, and when we talk about HALT, we say, we're going to go to the lab. We're going to push stresses.
Right.
Now, we may find stuff that's not relevant. It's not that it's already at the technical limit. It's just that it's part of the test fixture. It's part of, the interconnect for our sensors fell off. So that's a failure of that adhesive on the vibrating on the transducer or something. And then that's not a relevant failure. Let's look at what we're doing.
Right. And I talk about, the melting of a solder, taking a board operating to the melting point of solder.
Yeah, well, that's a technological limit. So that's not
a
relevant.
Technological limit. It's not relevant because it's
so far beyond your margin. Yeah.
Right. And if you could ever get it to work that high, then that's great. Congratulations.
Well, though I did run into one group that was insisting they needed to use low temperature solder. And I said, well, what's your operating environment? And it was like 10 degrees above the melt point of the solder. And I'm like, right.
I know.
You need to rethink this here, guys.
Right, exactly. But that you may have in a lot of designs where like the oil instrumentation, oil well, downhole oil well monitoring has to operate at 185 degrees C.
Oh, even higher sometimes, yeah.
So higher sometimes, 200. And so they have to use special solder. But the components, the semiconductors, have no problem operating at those levels, amazingly enough.
for not very long though. The guys I worked with on that, I mean, they would put this equipment in the cylinder right behind the drill head, essentially, right?
Mm-hmm.
And
right.
So it's encased in a steel tube. It's the electronics is all potted. I mean, it was just solid,
Right.
Right.
Mm-hmm.
And they did all kinds of exotic stuff to get it attached so that it would dampen the vibration and even out the temperature. They didn't want one end to be really hot and the other end not to be. And the big steel casing was a good way to do that. But they did a lot of things to make sure that it was seeing a uniform as possible stress. But those devices and 1 6-foot section of this thing would be like $1 million to use, right? To build and to use. And they would use it maybe twice.
Wow.
Yeah. So it would go down hole, get down in the hole, down, a mile into the ground, bang around for a couple of hours, come back out, maybe do it again. And that was it. They'd retire it. They'd rebuild it because their experience was that these things, and it was connectors, the interconnect parts, the stuff that was exposed to a lot more stresses and stuff. But your point about the electronics being able to survive this stuff was really good. But when it was all potted, and in order to do the repairs and everything else, you basically threw all that stuff away because there wasn't anything you could do to repair the electronics, even the interconnects and stuff. So
I have heard from a manufacturer of these kind of downhole monitoring systems that they had up to 4,000 hours operating with some of them.
Yeah, and it depends. The ones I worked with were right behind the drill string.
So they can be pretty durable if they, they compensate a little bit for the shift that the temperature does cause the product, or the timings or something to skew. But for the most part, they've gotten an amazing margin on them, and that's a lot of times in HALT. That's what's impressed to the engineers when they are willing to go, beyond the spec and keep step stressing, is they're sometimes very impressed with the margin that they didn't know they had, how strong it can be.
Oh, I totally agree. It's always fun. It was when I explain, the process, and I says, now I really need one or more of your designers or engineers that understand this product and materials at the lab. It's very important. And usually I get, well, why do you need them there? And he says, because when the beads of sweat start forming on their forehead because they know it's going to break, I know that we're getting close to where they considered a weakness. And so we'll keep going. And 9 times out of 10, it goes well past where they thought it would go. And they builds confidence that, they were being conservative. And then we get a surprise, a capacitor falls off or a screw backs out or, some other. Well, I never thought of that. I was like, that's why we're doing this.
No, it's the overlooked design limit, something that was not really considered and wasn't considered important at the time. But, I've had to tell engineer that was responsible for the product when I was taking it up in temperature, and he says, well, how far are you going to take this?
Until it fails.
I said, until it fails. I said, why don't you go back to your office and sit in, I'll come get you after it fails and let you know the results.
After the fire department comes and puts it out.
Well, that was his thought. It was going to catch fire, and I was going to have a bunch of melted metal and, epoxy, and that was it, so... fortunately, he found out that one of the 3 systems operated quite high margin, but the other 2 didn't have. It's quite a distribution of limits. So that in itself said you've got a very inconsistent design as far as these 3 models that are the same, and you've got temperature range of 40 degrees C between the worst and the best. So that's and. It's only using 3 samples. If I'd used more, I could have seen what the, statistical distribution was. But generally, they don't have that. You're working with one sample, one prototype.
Well, that's another fear I've run into is this is not relevant. It doesn't account for the variation from part to part. And it says, if you find one of your units that fails at 1 degree above your operating limit, that you expected operating, range is supposed to work in.
Right.
Do you need to know that the other one's going to fail below that point, or is that intuitive? One thing I like about HALT is that we usually don't talk about statistics other than explaining the concept, saying, hey, we're finding a limit. And we know that some of your units are worse than this and some are better than this. This is not an absolute first not everything will survive at 83.2 degrees Celsius and above or below, because we found one that failed at that temperature. No, it doesn't work that way, guys. We know that there's a spread. We want that margin.
Right. And that's what I think design engineers don't necessarily consider is, first of all, the distribution in variation in what could be the components, maybe the suppliers, and again, setting up ideal or the end-use environment conditions are going to be adhered to in every application that this,
it won't be adhered to by the first customer. It will not be adhered to by all customers. Easy to know that is not going to happen.
But then the design engineers, well, it's their fault then, right?
Gives them an out. It gives them an out.
Yeah, it gives them an out. Yeah, it wasn't ever supposed to be. This was a sequence and how you turned it on, and you turned it on wrong. And I'm going like, well, if that's that critical, then you would have made an interlock for the sequencing of the power up.
Yeah.
So
I always say that's an out. That's a way to go out of business if you just blame the customer.
Right. Exactly.
All right. So we ran into 4 or 5 different sources of this fear. I mean, and part of it is resources. Part of it is, what am I going to get from this? Part of it is, I don't need extra things to work on. I already have plenty. What if it's relevant or not relevant? And on and on and on. I'm quite sure there's some other ones in there. So let's ask our audience that, and, what do you see as pushback of dealing with people that, when somebody objects to doing HALT and you're maybe recommending it or you're suggesting it or want to explore it and you get pushback, did we miss any of those? Any sources out there that would be worth exploring a bit more? Or what's your techniques for getting around this or working through it? We'd love to hear from you. Head over to accendoreliability.com/go/SOR. You can leave a voice message, which, by the way, we got one that's related to an episode with Carl. We'll talk about that when I get a chance to talk to Carl again. And so we know it works. I actually got an email with the recording. It was way cool. You can leave us a voice message. You can leave us a written message. You can get a hold of Kirk and I and the other hosts of the show through LinkedIn or through our About pages. Lots of ways for you to get in touch with us. And we'd love to hear from you. So Kirk, I mean, we haven't talked about your ongoing HALT test with blenders lately, but so did you make it through the holiday so far without busting one of those?
No, we've had pretty good success with the kitchen appliances this year. So maybe we've run through the
the infant mortality parts.
Yeah, exactly.
Good for you. All right, Kirk.
Well, all right, Fred. We'll talk to you again soon.
All right, take care, Kirk.
Okay.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.